Hi, and welcome to C Programming for Arduino, a step-by-step guide. In previous video, we loaded and ran a program code to blink an LED. Let's look at this program in terms of our 5 program steps. This is the source code of the blink program. Source code refers to the series of C language statements that constitute the program. It is the source code that the compiler reads and checks for syntax and semantic errors, and ultimately translates into the binary code that is ones and zeros. It is the binary code that the microcontroller understands. First, we will discuss the program comments on the source code of the Blink program. If you look closely at these lines, you will see that none of the indicated lines end with a semicolon. If that is the case, then what are they and why are they part of the source code? The indicated lines are called comment lines. Comment lines are used to document what is going on in a program for whomever may be reading the code. There are two types of comments: single line comments and multi-line comments. Single line comments begin with a pair of forward slash characters. There can be no spaces between the slashes, as indicated. Otherwise, the compiler might think it was looking at the division operator. Upon seeing the two slash characters, the compiler knows that what follows from the two slashes to the end of the current line is a program comment and does not need to be compiled. It must be taken care of that comments that begin with double slash must appear on the same lines as the two slash characters. If you fold a comment to the next line without seeing the leading slashes, then it will be seen as a syntax error by the compiler. Multi-line comments begin with a slash asterisk pair and end with an asterisk slash pair. There are no spaces between the two character pairs. Everything between these two character pairs is treated as comment and is ignored by the compiler. Unlike single-line comments, multi-line comments can span multiple lines. It must be noted that comments invoke no penalty in terms of memory space on the performance of the program, so there is no reason not to use them as needed. Comments should be used anytime you wish to document what a program is doing or about to do. Reading code without comments is not always easy, and it might be hard for the reader to figure out what's going on in a particular section of the code. In such cases, a comment may make it easier for someone to decipher what the code is supposed to do. For example, if you have a function block that implements some really scary mathematical equation, then you might add a comment to explain what is going on. If the function is really complex, then it is not uncommon to put a multi-reference comment into the code that has a book page number or perhaps an internet URL address where the reader can go for further information. Mostly it seems that comments are directed to someone other than the person who actually wrote the code. Frequently that is true, but especially if you write code in a commercial environment with other programmers who may have to work with your code. However, even if you are the only person who will ever see the code, you would be amazed how a piece of code that was so easy to understand this morning will be very difficult to understand in 6 months from now. Therefore, comments should be used to help the person reading the code, whomever that may be. Too few comments often makes the code difficult to understand. There are simply not enough comments to be helpful to your understanding of the code. However, too many comments can have the same effect because they get in the way of understanding the code. Comments are clutter if they do not contribute any real benefit in understanding the code. First part of the code presents a short comment telling the reader that the setup function is called once you reset the program. This is a characteristic of all Arduino programs. Every program you write will have a setup function in it. Setup function marks the starting point for all the Arduino C programs. Where standard C always starts program execution with a function named main, it is setup that marks the program's starting point in Arduino C. Because setup is the starting point for all Arduino C programs, it also becomes the initialization step in our 5 program steps. The purpose of the setup function is to establish the environment in which your program will run. In this case, the initialization step does nothing more than defining the built-in LED as output mode. Many boards have built-in LED to test being programmed, and in most Arduino boards, this LED is also connected with the digital input and output pins. In case of Arduino Uno, we have a built-in LED and it is connected to digital pin 13. By defining the built-in LED in output mode means that digital input output pin number 13 is configured as an output pin, which will output 5 volt at regular intervals in parallel to the built-in LED. We can connect an external LED with pin 13 in order to make it blink. It establishes this mode by calling a pre-written function named pin mode and passing the information that the function needs to perform its job as arguments to the function, which means that pin mode evidently needs to know two things that exist outside its function block. First thing is, which pin does the programmer wish to set? In this program, programmer wants to set built-in LED, which by default sets the digital pin 13. The second thing pin mode wants to know is, does the programmer wants it to function as an input or output pin? In this program, programmer wants the set pin to work as an output pin. It means that we want to use the output from the pin to control things rather than input values from the outside world via the pin. It is important to remember that setup function is only called once when the program first begins execution. This is why we can refer to the setup as an initialization step in our program. If you wish to call the setup a second time, then you would have to press the reset button on the microcontroller board. Reset button halts or stops the current execution of the program and restarts it by calling setup. The setup function is automatically called each time you upload a new version of the program from your PC to the microcontroller board. The second argument in the function is output. It is a symbolic constant and can be thought of as a variable name that is embedded within the compiler. A symbolic constant is a name that is tied to a specific data value. There is a convention where symbolic constants are written in the uppercase letters. You could define a variable named output in a small letters, but as the C language is case sensitive, the compiler knows that it is a different variable than its own symbolic constant named output written in uppercase letters. Symbolic constant makes the program code easier to read. Consider the following example. Which one is easy to understand as output? This one or this one? So in simple words, symbolic constants are a series of uppercase letters that are tied to some predefined value. After the setup function completes its work, every Arduino C program automatically calls the loop function. In other words, when the initialization step is completed by a function call to setup, we are ready for step 2, the input step. Inside the loop function, the program calls a pre-written function named digitalWrite, which has two arguments. First is the pin number as stored in variable built-in LED. Second is the state into which we wish to place the pin, which is high in this case. Once again, high is the symbolic constant held within the compiler and is interpreted to mean that we want to turn the pin on, which supplies a voltage to the pin. This voltage then turns on the internal LED and also external LED, which is connected to pin number 13. So digital write serves following purposes. It tells the function which input output pin to change and what state to place input output pin in. Once the function receives these two pieces of information, it places the LED in the desired state. In this case, function turns the LED on. In other words, passing two pieces of information to the function, digital write serves as the input step of our 5 program steps. Digital write also serves as a part of the processing step because it takes the input data from the input step and changes the state of the LED according to the inputs it just received. Given these inputs, the LED is turned on at this point. That is, LED displays the output. The delay function call causes the program's execution to pause for 1000 milliseconds or 1 second. Because the LED is turned on, this has the effect of letting us observe the LED with illumination. If the call to delay function was left out of the program, then LED would be turned on for such a short period of time that our eye would not even be able to tell that it was ever on. Therefore, the delay function call serves as an extension of the output step of our 5 program steps by letting us observe the current state of the LED. Next, digital write function is called with delay function, which turns the LED off for 1 second. This is still part of the process and output steps. Turning the LED off is just as much a display process as turning it on. Once the delay function is finished, the closing brace of the loop function is read. However, because loop establishes what is called a program loop, program execution returns back to the first statement in the loop and performs a second pass through the loop starting with digital write again. This turns the LED back on. This sequence is repeated until the power from the circuit is removed. It means that the LED simply sits there and blinks until the power is removed from the microcontroller board or a component fails. Because the program is designed to loop forever, therefore there is no termination step. Most microcontroller programs are written to run until they are stopped by some outside force. There are exceptions to this generalization, but they are relatively rare. In previous videos, we have seen the LED blink code working on built-in LED. Now let's see this code working on an external LED parallel to the built-in LED. For this purpose, LED must be connected to Arduino board according to the given circuit diagram. In this diagram, positive pin of an LED is connected to pin 13 of Arduino board through a low value resistor, and negative pin of LED is attached to the ground on Arduino board. Let's see it working. This is the built-in LED. This is an external LED. You can see that both LEDs are synced perfectly because built-in LED is connected to the pin 13. Note that LED turns on for 1 second and turns off for 1 second, which produces the blinking effect. Now we will change the delay from 1000 millisecond to 3000 millisecond. You can see that blinking has become slow. Let's change the delay from 3000 millisecond to 300 millisecond. Now you can see that the LED is blinking faster. So that's all for this video. We will continue learning in the coming videos. Till then, take care and goodbye.